Hey everybody, and welcome to these video notes on heating curves. In particular, the other day we discussed in class the shape of this graph that you're seeing above and what each portion of this graph represents in terms of phase changes of something like water. To remind you of some of the things we discussed, we have blue regions on the graph, which I've highlighted, which represent heating and cooling. When we heat or cool water, it changes the speed of the particles. Heating water means you are speeding the particles up and increasing the temperature. When you're cooling the water, that would be in the opposite direction, so heating would be up the graph like so. As we are cooling water down, we are going back in the other direction down the graph. And basically what we're saying here is when we're cooling, we are taking energy out to slow the particles down and cool down the temperature. Those are the things that are happening there. We're cooling it by removing thermal energy. We also have two yellow sections of the graph, which you can see here as well. These are where our phase changes occur. In these phase changes, the particle spacing is going to change, meaning that from B to C and D to E, the particles are either getting spread apart or brought closer together. However, it is at these points that there are no changes in temperature. You can see right here across to the y-axis of this graph that there is no temperature change. The graph plateaus or flattens. It is important to note that today we're going to talk about the math behind these parts of the graph. And it's important to note that anytime energy is added, our values are going to be positive. And anytime energy is removed, the values will be negative. What this basically should remind you of is a bank account. When you add money into your bank account, you get a positive value, you feel positive, you're happy, you're saving money, and the bank tells you you have a positive balance. When we remove energy through the process of cooling, our values will be negative. Just like if you take money out of the bank to pay your bills or whatever, you feel sad, and the bank gives you hopefully not a negative balance. So that's something important to keep in mind. Most of the calculations we'll do are going to be adding energy into the system and therefore be positive, but every once in a while when we cool things down, we will see negative values appear. We are going to be doing two calculations today, and this is the easier of the two, at least for most people, and that is the calculation associated with these heating portions of the graph. Remember, this is the part where we are going to have a change in the thermal energy and therefore a change in temperature as a result of the particles speeding up or slowing down. The equation for this is seen right here. Q, that is the letter Q, if you can't tell because the little tail got cut off. Q is the energy. I'm going to write energy up here. So Q is the energy. Why they used Q, I don't know. Remember, Q is measured in joules. This M is going to be our mass, which is going to be measured primarily here in grams. This whole part here, the triangle T, which I'm going to sort of highlight here, this whole part is what we call, or what you will hear me referred to as delta T. Delta is a Greek symbol. Basically, it means change in T, or temperature. Delta T is going to be measured in degrees Celsius. And when you see that delta T, what you should think of in your head is to find the change in temperature, we take the final temperature of whatever the water or substance is, and we subtract the starting or initial temperature. So delta T is just a shortcut for writing final temperature minus initial temperature, and that's what the TF and TI stand for. Now we've got joules, we've got grams, and we've got degrees Celsius. Those are kind of weird units, at least separately. So we have to introduce a constant here. This constant is represented by the letter C. This is what we call the specific heat. Whoops, I'm going to do that on the other side to be consistent, or at least attempt to. Specific heat. The specific heat has a unit of joules per gram degree Celsius, or joules over grams degree Celsius. You will notice, if you think about this in the way we've been thinking about our stoichiometry, you'll notice that this grams degree Celsius is on the bottom of a fraction. These would be on the top of our fraction, and it causes these units to cancel out on this side of the equation. That leaves us with joules. So you can think of the specific heat sort of as a way of making the units in this equation work out nicely together. The specific heat is the amount of energy required to heat 1 gram of a substance by a degree Celsius. That is how it's defined. So not only is it just a useful number to have in an equation, but it has a very important definition. And again, that's the amount of energy required to heat 1 gram of a substance by a degree. To give you a picture of this, I'm going to kind of sketch this out. Let's say we have a gram of water. Let's just say we have a gram of it. We'll draw it like a cube. You can draw it like a square or a circle or whatever. We have 1 gram. And let's say that we have a thermometer there. Some kind of thermometer reading a temperature of like, I don't know, 10 degrees Celsius in this block of water. If we add to this 4.18 joules of energy, maybe it's from like fire, maybe it's from like a hot plate, we add some heat, doesn't matter from where, or energy. 4.18 joules of energy will take our 1 gram block of water, which I'm going to redraw here, 1 gram block. Sorry, my cube is very ugly looking. And what that will do is it's going to raise the internal temperature to 11 degrees Celsius. That's what this number tells me. 4.18 joules of energy in to raise the temperature of 1 gram of water 1 degree. Likewise, if we wanted to cool it back down, if we wanted to go the opposite direction, we would have to remove 4.18 joules. So it does work in both directions, heating and cooling. You do need to sort of have a conceptual understanding of what this ends up being. Alright, if anybody needs another second, this would be a great time to pause. We're going to do some practice problems now. You will notice that I always approach these in the exact same way. This is the way that I would expect you to approach them on tests and quizzes. This is also the way to approach a physics problem should you be taking physics next year. So, the first thing you should notice is you're going to be heating up a substance. Nowhere in here does it talk about phase changes yet. So, it says how much energy does it take to heat 4.1 milliliters, 1 teaspoon of water from 20 degrees to 37 degrees. Now, normally I would give this number to you in grams. So, if you don't remember that a milliliter of water is the same as 1 gram, that's not information you necessarily need to know. I just sort of let it slide in here. But basically, 4.1 milliliters of water is going to be equal to 4.1 grams. We are going to see how much energy it takes. So notice we have some number in grams. That's going to be our mass. Notice we have some change in temperature. And we're always going to know the specific heat of water. That's going to be a constant you will be given on tests and quizzes. You do not need to memorize it. The first step to doing this problem correctly is to write out what I call the naked equation. And that is the equation you will be using to solve the problem. We always start here. Why? Because I said so. Now, at this point, we are going to do some plugging in. We are solving for how much energy. Remember, how much energy is Q. We will plug in our specific heat of water, 4.18 joules per gram degree Celsius. Yes, you need the unit. Why? Because I said so. Mass is going to be next, 4.1 grams. And lastly, delta T. Remember, delta T is the final temperature minus the starting temperature. Okay, so remember that's T final minus the starting temperature, or T initial. So our final temperature, we're going to 37 degrees. And we're going to subtract off our starting temperature, which is 20. So notice all the units are in there, degrees. If we want to be real technical, which I'm going to be, we can add the little C for Celsius. And notice, when we do this, 4.18 is positive, 4.1 is positive, and the subtraction step here is positive. We're adding heat into the system, and as a result, we're getting a positive value. When we multiply these three numbers together, 4.18 times 4.1 times 37 minus 20, we should end up with 291.3. The unit here, if you again forget, joules and grams in degrees Celsius on the bottom, grams in degrees Celsius on the top, cancel out, and we're left with the unit for energy, which is the joule. So that is my answer for the first problem. Again, pretty plug and chug. Second question says, this one's going to be a little more complicated. It says Mr. Bear's microwave is able to pump in 175 joules of energy into a 100 milliliter glass of water. What is the change in temperature? So remember, change in temperature is represented by delta T. So we're going to be looking for the whole value of delta T. In the second part of the problem, it will give us our starting temperature, and we're going to look for our final temperature. So we'll do that in step 2. Like always, I'm going to start with my naked equation, Q equals Cm delta T. This one, we're going to be solving for delta T. So we have Q, 175 joules, is equal to 4.18 joules per gram degree Celsius, times the mass, which is, again, 100 milliliters is 100 grams. I promise you I will give you your numbers in grams from now on. I promise, I promise, I promise. If you forget, they're the same number. And we're going to solve for delta T. When we plug in these values and multiply and do some division, we get a delta T value of 0.42 degrees Celsius. And we get that by doing 4.18 times 100, and then we divide it across. So that would be 175 divided by 418. So we get a change in temperature of just under a half a degree Celsius. It's not a lot of energy. It is a lot of water. And it says if the starting temperature is 25 degrees Celsius, what is the final temperature? So remember, delta T is going to be equal to the final temperature minus the initial temperature. So delta T is 0.42, is equal to T final minus 25 degrees, and that gives us our T final of 25.42, which you probably could have done in your head, but there's all the nice work for it. So, these are examples of, again, just to remind you, these are examples of heating and cooling substances. But this is not going to work for phase changes. And we're going to see how to deal with that next. Now, the first thing you should think about when you hit phase changes is that previous equation is going to break down. The reason that breaks down specifically is if the equation is Q equals Cm delta T, notice in our phase changes, delta T, or the change in temperature, is 0. So this whole equation breaks down. Why? Because otherwise everything here would be equal to 0. That's not going to really work. So we need a different tool. The tool we're going to use, actually two of them to be specific, are called enthalpies. Enthalpy is a fancy word for energy. Why there's a different name, I don't know. I've looked it up. I don't remember. There are two enthalpy values we're going to use. The first one that we're going to see is called the enthalpy of fusion. Basically, the enthalpy of fusion is the amount of energy to convert 1 gram of solid water to liquid water. Basically, it's the energy used in this particular section of the graph. The energy it takes us to go from point B over to point C. You can note or remember this because the word fusion appears in small letters next to the delta H. The delta H itself is the symbol for enthalpy. Again, probably a little confusing, but you'll get used to it. The enthalpy of fusion for water is 333.55 joules per gram. So similarly to our Q equals Cm delta T, if I have a gram of water, I'm going to go with the two-dimensional cube because I'm lazy at this point. If I wanted to increase the temperature of this enough to go from ice to liquid water, so solid to a liquid, this would take 333.55 joules of energy. Likewise, if I had liquid water and I wanted to go backwards, it would take an equal amount. So that's the enthalpy of fusion. That is not the same amount of energy it takes for something to boil. For this, we turn to the enthalpy of vaporization. Vaporization tends to be a little easier for people to remember. Why? Because water, vapor, evaporation, it sounds like that. This corresponds to the section D to E in the graph above. So notice that is the energy to convert 1 gram of liquid water to gaseous water or steam. Something you should notice whenever we draw these phase change graphs is that the enthalpy of vaporization for water, the number boxed in here in red, is much bigger than the enthalpy of fusion. And you do need to know why. Remember, during a phase change, all of the energy is going into spreading the particles out. They're not moving any faster, they're not getting any hotter. Particles are just being pulled apart from one another, overcoming those attractive forces. When you're thinking of a phase change, something that I can draw out pretty easily here, if we're going from a solid, which that's a really crummy solid, but we can make it work, if we're going from a solid over to a liquid, we are taking into account this enthalpy of fusion. That energy has to go in to this process right there. That is not a major separation. The liquid particles are still pretty close together. To go from a liquid, however, to a gas, this process takes a lot more energy because the particles are being separated so much further. This is why the enthalpy of vaporization is like 10 times bigger than the enthalpy of fusion. So that's something you need to know. Again, it's bigger because the separation in particles from a liquid to a gas is a lot greater than the one from a solid to a liquid. Now, using the enthalpy of fusion and the enthalpy of vaporization is actually very simple. However, it is going to use a skeleton. We're going to approach this with some stoichiometry-like ideas. The thing you are going to like about this, though, is it's going to be a lot shorter, because I've given this to you specifically in joules per gram. Other teachers, who maybe aren't as nice, could give this to you in kilojoules per mole, adding like 2 more steps to the problem. I'm going to stick with joules per gram because it's nice and simple. So, the first question says, how much energy does it take to turn 15 grams of ice into 15 grams of water? Remember, if we're going from ice all the way to steam, we said the numbers will be positive. Why? Because we're adding energy. If we're going backwards, the numbers are negative. This is going to be where that comes into play, because if we're going to subtract energy, what we're going to have to do is put a negative in front of these numbers whenever we are cooling things down. So just keep that in mind. In these two examples, we're going to be heating. So again, how much energy does it take to turn 15 grams of ice into 15 grams of water? I'm going to start with a skeleton here, and I'm going to start with my given information from the actual problem, which is 15 grams of ice. There it goes. And I'm going to put that in the skeleton, 15 grams of ice. It doesn't really matter what the substance is. The water part here is not really going to be important because we're not going to be changing substances. But we'll put it there just because we're used to it. Now, at this point, we're going to use our enthalpy to do the calculation. The key here is remembering which of these two numbers to use. Because we're going from ice to liquid water, we are going to use the enthalpy of fusion. Notice how the unit works just like a molar mass, and that we can take 333.55 joules and put that over 1 gram. This makes the grams cancel out and leaves us with joules for energy. So it's a really nice one-step process that will only take a little bit of multiplication and division. When you do this calculation, you do 15 times 333.55, and you get approximately 5,000 joules. You get 5,003 and a quarter joules. That's a decent amount of energy. I don't know how many calories that is, but it's a decent number. I don't like how that kind of looks like a 15. There we go. Better. Meh, sort of. Maybe I just won't box it in. There we go. There's the answer. We're going to do something similar for the one below. It says, how much energy does it take to take 15 grams of water and turn it into steam? So when we're going from water to steam, we're going to be using vaporization. So we take our 15 grams of water, and we're going to multiply it this time by the enthalpy of vaporization. So 2260 joules for every 1 gram of water. They cancel the units out, and you do the multiplication, which I'm going to do right now. Instead of pausing the video, I'm just going to type it into my calculator. And you get 33,900 joules. So again, because we're separating the particles so much more, going from a liquid to a gas, same amount, 15 grams, a lot more energy required. That's, again, a major takeaway here. Last problem here we're going to approach is what I like to call a combination problem. And this says how much energy must be removed. So keyword there already popping up is going to be removed, meaning that, again, when we take energy out, it's going to be a negative value. From 200 grams of water at 15 degrees Celsius to turn the water into a solid block of ice at -5 degrees. Now, the first thing you need to do when you're looking at something like this, there's a few things that should stand out to you. First of all, 15 and -5 degrees Celsius. You should notice that somewhere in between here, 0 degrees Celsius occurs. That's something that immediately should stand out. Remember, 0 degrees Celsius is the freezing point of water. Meaning, something kind of weird must be happening somewhere in here. The second thing that jumps out at me when I do this is it says turn the water into a solid block of ice. So something like this is what I like to call a combo problem. Because in this problem, we are going to be using multiple equations up here to find the total energy of a chunk of that graph we've been looking at. So let me draw this out for you right now so you can kind of get an idea of what we're looking at. Remember, the graph looks like this. I'm going to zoom in just for now so that way I can draw it nice and neatly. Remember, the graph looks something like this. We've got a heating of the solid, we've got a melting, we've got a heating of the liquid, we've got a boiling, and then we've got a heating of the steam. In that order. What we will notice here in the problem, I'm going to highlight it here just to make it a little more noticeable for when I zoom out again. It says how much energy must be removed from a 200 gram block of water, 200 grams of water at 15 degrees Celsius. So if we, again, I'm going to zoom in on my graph here. 15 degrees Celsius is somewhere around here on the graph. So we're going to start somewhere at like 15 degrees Celsius, and we're going to cool this into a solid block of ice down here at negative 5 degrees Celsius. So notice, something that should immediately stand out to you in this problem is we have a part of the graph that's slanted, we have part of the graph that's flat, and we have part of the graph that's slanted again. So we have three different segments of this graph. Unfortunately for you, and I guess for me, because I'm going to do this problem with you right now, is that means we have to do this in three pieces. Meaning we are going to have to do a cooling portion for portion number 1, which again, I'm a little bit zoomed out now, so it's going to be kind of tough. Let me try and zoom in again. We're going to have to do a cooling part for portion number 1, which is this slanted bit right there. We're going to have to do an enthalpy part for this flat bit there in the middle. And then we're going to have to do another cooling part for segment 3, which is the cooling of the ice down to negative 5 degrees. So we're going to have to do 3 different calculations, and we're going to have to add them all up. Plus, this is a cooling or removal of energy, so we're going to have negative numbers. Okay, I'm going to take a nice deep breath, and we're going to do this. And I'm relatively calm because I really know how to do this. But hopefully you're also taking a nice, calming, reassuring breath. And Miss Sands is taking a nice, calming, reassuring breath. And we're going to get through this. So, step number 1. We're going to deal with the cooling of the water from 15 degrees Celsius to the freezing point. Remember, cooling of water is going to refer to our Q equals Cm delta T equation. The Q is what we're solving for. We know that the C of water is 4.18 joules per gram degree Celsius. We're going to plug that in. We're going to plug in our mass of our water, if I can do these parentheses correctly, which is 200 grams of water. And then remember, delta T is just temperature final minus temperature initial. So the final temperature of this cooling portion of the graph is going to be 0 degrees. Why? Because at 0 degrees, we have to use a different type of math. So we're going to do the 15 to 0 degree part first. So our final temperature for this section is 0, and our starting temperature is 15. Notice, when you do this math, very simply here, you get a negative number. That's going to help us, that negative, come up with a negative Q value. And that means this Q will be negative, if I haven't said it enough. So, we are going to plug this into our calculator. We are going to do 4.18 times 200, 4.18 times 200, times negative 15. And what you end up with is negative 12,540 joules. So that's part number 1. That is the amount of energy it takes to do this first little segment on the graph, the first slopey bit. Then we are going to do segment number 2, which is going to be our freezing component. For that, we are going to turn to enthalpies. Remember, when we're talking about freezing or melting, we are going to use the delta H of fusion to do that. So, 200 grams of water is what we're starting with. Truthfully, you can actually start with the enthalpy of fusion. In your skeleton, it works out just the same. So it's really up to you. I like starting with the mass because that looks more standard to what we've been doing so far. We're going to multiply that by 333.5, and that will give us the amount of energy it actually takes to freeze. Now, again, when you do it with the skeleton, the number you get will be positive. You will get 79,240. It is your job to know that because we're talking about freezing, because we're talking about removing energy, that this is going to be a negative value. Not an equal value, a negative value. That's our second step. That's our flat part in that little graph way up there. Lastly, we have to deal with the cooling of the ice. Oh my gosh, it's so much work. I can hear Ella in third hour complaining about it already. Just kidding. And if it's sixth hour, that doesn't even apply. I don't even know why I made the joke at this point. There's a lot of numbers. All right. So, last part. We're going to do Q equals Cm delta T again. For our cooling of our ice. This last third little bit on the graph. So, again, our C, right now, we're going to assume that it's still 4.18 joules per gram degree Celsius. Once water turns into ice, this number, this C value, actually doesn't work for ice. But that's a story for not at this exact moment. That's a story for you to realize when you get to your homework worksheet. We're going to plug in our 200 grams, and we're going to plug in. We're starting at 0 and ending at -5. So that's -5 degrees Celsius minus 0 degrees Celsius. This will give us some number. I don't know what that is. Let me type it in. 4.18 times 200 times -5. 4,000. -4,180 joules. So if I want to find the energy to do this whole process, this whole section of the graph up here, this whole thing right there, what we need to do is add all these numbers together. So we're going to do that, and then I'll talk a little bit about that other C value. So, at this point, the total energy is going to be -12,540 minus 79240 minus 4180. 12,540 minus 7, 12. I'm going to pause this so I don't bore you with my calculator. I'm currently getting -95,960 joules as the total amount of energy to make this process happen. So, there it is, 3 steps. You will be responsible for being able to pick out a couple problems where you might have more than one step, and then being able to add them together. The last thing I want to say before I turn this video to its end and turn you loose on some practice is I just noted a few seconds ago the C value, whoa, alright, only certain things are zooming there, so I'm just going to try and get to a normal spot. The C value for different substances like water versus ice are going to be different. So typically the value isn't going to change all that much between water as a solid and water as a liquid, but on the worksheet you see tonight for homework, the worksheet you see tonight for homework, it will list 2 different specific heats, one for water and one for ice. All you need to do is, if we're talking about something like liquid water, use the 4.18. That's what we're going to be using most of the time. If it's something solid or gas, you will use the value provided on the homework worksheet. Alright, so this wraps up a lot of math. So please take a few minutes either now at the end of the hour or tonight to work on the practice I have left you. And you will get to see the key and ask any questions of, I guess, each other tomorrow in class. Alright, have a great rest of your day. Hope this wasn't too boring, and if you need anything, you know where to find me. Twitter, Schoology, Snapchat, wherever you need me, find me. Bye.